Hello everyone, welcome to another video from Biology. So in this video I want to talk about self-supervised learning from images with a joint embedding predictive architecture. This paper has been contributed by Meta AI, McGill University, and Quebec AI Institute and New York University and published in January 2023. So this paper is famous as I-JEPA. There is also another report by Jan LeCun, JEPA for like future of AI. So many people think that this is like the first real like implementation of that for the self-supervised learning and like creating artificial general intelligence. So let's see how it goes. Basically, for self-supervised learning, we have uh, architectures like this. It's called joint embedding architecture. So how is that? If you have seen one of my video, it's bootstrap your own latent, one of the like I can't say now oldest techniques for the self-supervised learning. You see that we have a model. Sometimes this can be a teacher, this can be student or stuff like that. But in this case, we are just doing the self-supervised learning. So we have a model and we want to train this model uh, somehow to learn the data distribution or the latent distribution behind the data. So, or learn the inductive biases per se. So we have a model and we pass an input to the model and it can generate us some latent representation or embedding. In some of the self-supervised learning, we do the exponential average or we just I have a copy of this model somewhere else here as a Y. And here we need to apply augmentation on this image. So we have X, apply some augmentation, convert it to Y. So basically it's same image, but has different kind of changes on the image using augmentation technique. And then we apply it on the similar model, same model. And we are generating a new representation, but because the basic like the images we are passing to these models are same, we expect to get the similar representation. So that's why we try to discriminate between this SX and SY. So we are discriminating between these two. This discrimination should be low for images that are coming from same source but having different augmentation. And some other techniques and some other paper also adding some of the images. It's like CMS neural network that you want to increase the distance between the representation of two different images if they are really coming from different uh, like classes, like in few-shot learning. So this is the old technique for self-supervised learning. In generative architecture, we are doing differently, very similar, but we are doing that differently. Suppose that we have GAN, for example. So that is a generative architecture. So we have an input and we have an encoder decoder. So suppose this is a like a GAN model here. And then we have some latent representation, some help for the model because this is generative architecture. We need to like feed some latent variable here to facilitate reconstruction. And then we are comparing it with the output that is a discriminator part in the GAN methods. Not only GAN, but even if you look at the like LLM or the auto regressive model, you're seeing the similar pattern. So you have the input and you pass it through the encoder or decoder. Suppose this is T5, so we have some sort of cross attention here. And at the end, what we want to do is we want to like reduce the distance between what it is generating with what we expect. But joint embedding predictive architecture is something that is claimed to be introduced in this paper. And I say claim because when I explain this, I can remember some of the models that already exist. For example, the methodology for currently people are using for evaluating the reasoning of generative architecture like GPT model. So this is joint embedding predictive architecture. So we have input, and again, this can be the decoder. This is called predictor just because the name has the predictive inside. And we have some latent representation to help facilitate reconstruction. But here, instead of just comparing the output with the target, we have some encoder on the target, and then we compare them. So what is the difference? Let's look at the abstract. This paper demonstrated an approach for learning highly semantic image representation without relying on handcrafted data augmentation. We introduced the image-based joint embedding predictive architecture, I-JEPA, a non-generative approach for self-supervised learning from images. So basically this paper is focusing on images, but the idea can be extended to language models and NLP domain. As I explained that there are some other researchers going on doing this. And just before going further, compare these together. For this one, we need augmentation. For this one, we don't need that augmentation. We are like giving some input to the model and some hint, and then we are expecting to get the output. We are not augment anything. We can, but basically we don't need to. And in this method also, for joint embedding predictive architecture, we don't need to do augmentation. So here it said, the idea behind I-JEPA is simple. From a single context block, predict the representation of various target blocks in the same image. A core design choice to guide I-JEPA toward producing semantic representations is the masking strategy. Specifically, it is crucial to first predict several target blocks in the image. Second, sample target block with sufficiently large scale, occupying 15% to 20% of the images. And third, use a sufficiently informative, spatially distributed context block. Empirically, we combine with Vision Transformer, we find I-JEPA highly scalable. For instance, we train a VIT huge 16 on ImageNet using 32A100 GPUs under 38 hours to achieve strong downstream performance across a wide range of tasks, inquiring various levels of abstraction from linear classification to object counting and depth prediction, just by using self-supervised learning. So let's go to the ideology that it's explained here. So here is the I-JEPA. So instead of augmentation, as you see in this architecture, what Otter is doing here is they are like first selecting a portion of the image, a large portion of the image as a context, and they pass that to the encoder. So we have the encoded part of a large portion of the image. We call it context or embedding of the context. Then we have some target window. Okay, and what we are going to do is, let me go down, there's a better picture here. What we're going to do is we select some target here. These targets shouldn't overlap with the context. You see that there is no overlap with the context. They can overlap with each other, but they can't overlap with the context. So what we're going to do is, from this context, we want to reach to these targets. So that is I think this is like a smart idea, because previously we could apply different kind of augmentation on this original image, and that depends of the severity of augmentation, stuff like that. There are many ablation studies done on like how we can justify how this augmentation is good. So this work that we have a context, so I can like generate, for example, from this original image various contexts and targets. So I can somehow, using this technique, I can extend my dataset size. If I have, I think, a few, comparing to very large dataset, if I have a few samples, I can at least start training using this self-supervised technique. because every time I can select different part of the image as a context, and also the targets can be various. So this is the whole idea of the technique. Basically, what they are showing here is, so we have this encoder, and they have also a target encoder, and they are showing, I think somewhere they mentioned that they are using the exponential moving average. Let me go to the methodology. Yeah, let's go to the methodology. Maybe we can read some part of this together. So they said, we now describe the proposed image joint embedding illustrated in figure 3. The overall objective is, given a context block, predict the representation of various target block in the same image. And they use VIT for the context encoder and target encoder. So just be careful that we have a context encoder and target encoder. And there was some points also here. I will talk about that. I should remember that. What was that? It was related to the loss, like how define loss. It is defined on the image part, or this is defined on the embedding part. So let me let us read, because I have read this paper about like 2 months ago, about like 2 months ago, yeah. And a VIT is composed of a stack of transformer layers, each consisting of a self-attention operation followed by a fully connected MLP. Our encoder prediction architecture is reminiscent to generative mask autoencoder. So mask autoencoders, if you remember that in that method, we usually mask some of the pixels, and we try to like generate those pixels. Some people are, it's very similar if you compare it with what we have explained in some other videos, like UL2 strategy for the uh, language model training. So this is different training paradigm for images like MAE, this I-JEPA. So let's see. It said we first describe how we produce target in the I-JEPA. So we don't need to go through this because they are like windowing, trying to be non-overlap. I explained some of this. And they call this the blocks. We do not BI, the mask corresponding of the ith block, and by SY, it's patch level representation. Okay. So they define like what is context, how they have defined context, and prediction. Given the output of the context encoder, which is called SX. So let me go somewhere I can see this. So they call this SX. It was better that if they could write this notation on the image. So they call that SX. We wish to predict the M target block representation to that end for a given target block corresponding to the target mask BI. The predictor, okay. Yeah, one thing I forgot is that, so we want to predict this target. We should say, this is the context, predict this part. I only have this context, but I only want this part. This is one target. So that is the part we are calling here as Z. These are the masks, like some latent representation that facilitate the generation. So here, again, you see that we are passing the mask here. So we are saying that predict this part of the image for me. So here they said, to the target mask BI, the predictor takes as input the output of the context encoder, SX, and a mask token for each patch. We wish to predict MJ and output a patch level prediction. So what the prediction is predicting is not the image, but it is the embedding. So that's the point. So it is the embedding that is getting predicted. And let's go down. The mask tokens are parameterized by shared learnable vector with an added positional embedding. Since we wish to make predictions for M target block, we apply our predictors M times. Each time conditioning on the mask token corresponding to the target block location we wish to predict and obtain prediction. Okay, so they apply it like if we have 4 target, they apply it 4 times. And I'm not sure that if like the output of one predict is it autoregressive prediction, like if I predict something here, am I using that for predicting the next block? I don't think so. Context is same, so we just apply it 5 times, so we will apply it 4 times, so we will have 4 different prediction. Okay, so far. The loss is simply the average L2 distance between the predicted patch level representation and the target patch level representation. Okay, so and they are just like taking the average for that. So if we have M, so they just, after calculating this embedding for each target part, so they are just calculating the L2 distance between the embedding predicted for the patch or for the target and embedding coming from the target encoder. Okay. Oh, where were we? Yeah. The parameters of the predictor and context encoder are learned through gradient optimization, while the parameter of the target encoder are updated by an exponential moving average of the context encoder parameter. And the use of that has proven essential for training GEA with vision transformers. So there are some other methods that use that exponential moving average. So actually we are using exponential moving average for updating this. So this is basically the same network. That can be a different size, but basically the same architecture. So we have so far the loss and everything. And that's it. I think they then go to the related work. So how do you want to use this? So we have the context encoder and we have the predictor. And uh, like each time we are predicting something, so we only have one predictor. You can see here that we don't have like multiple predictor. We have only one predictor. So every image we are, for example, for this case, we are updating predictor 4 times. And that's one of the reasons that the predictor would be powerful. So at the end, they are comparing it with some other method like data 2-vec, MAE, also method that use extra view data augmentation. So these methods do not use data augmentation like MAE because we just mask some of the pixel, and data 2-vec similar. But for other methods like SimCLR, I think this is Bootstrap around latent, Dino, uh, like this one, Bootstrap around latent, is that the paper we explained, I think, about a year and a half ago. So you see that this new technique, the VIT, is much better. Sorry, the I-JEPA is much better than the other methods. And like in methods that they are using augmentation, so we need like defining different augmentation. I feel that this kind of method is also taking less computation. Okay, and they are talking about like image classification, how it's working on image classification. The result is really good comparing to other techniques. For some of the methods, like for image classification, or I think this is for local prediction. For local prediction, you should see sometimes like the augmentation techniques are working better. But like for linear probe, this one is linear probe transfer for low level tasks. So these MAE is getting better. That depends on like what the specific downstream task we are working on. But overall, that's a good technique. And as I said, the computationally, it is better than other techniques. And yeah, they are showing some of the images that target can be generated differently. They are showing visualization of the predictor of representation. And they are doing some ablation study, like why they are doing the multi-block. And yeah, that's it. Overall, it's related to this self-supervised technique. So they are also comparing it with the MSN, one of the latest method. And one of the other thing I wanna talk here is about I-JEPA. So if you search for I-JEPA, you will find this, the first AI model based on Jan LeCun vision for more human-like AI. So he published a paper or report before this paper. And you see that it said the first model based on Jan LeCun vision. So there was a vision there. I think we can find it. I think even uh, Yannick Kilcher has some video about that. But there is official uh, repository for implementing that, and should be straightforward. Also, you should see that Lucid Rain I-JEPA. Yeah, it could find the JEPA PyTorch. Yeah, this is the main like paper, the path toward autonomous machine intelligence by Jan LeCun. And also there is a video about like uh, what is the like future predictive architecture, joint embedding predictive architecture. But overall, if you want an implementation, Facebook has an implementation. You can use that for the training. And that's the idea of the paper we have discussed. I hope you enjoyed the video. Please subscribe, put a comment, and share with your friends. Thank you.